Tuesday! Happy Tuesday! I hope everyone's doing well. I also hope my fellow United Statesies people, freaking statesmen, stateswomen, I hope you guys enjoyed your Labor Day. I hope you enjoyed your day off. I enjoyed my day off. I did nothing. I did absolutely. I did a load of laundry, but besides that, I did nothing. I didn't even leave my house. It was excellent, and not productive. I did not labor. Did not do any labor on Labor Day. I hope you guys also had to do little to no labor on Labor Day and you enjoyed your time off. I hope you guys also enjoyed your time off. Hi, Penboo. Wait. You didn't enjoy Labor Day, but you did have a good Labor Day? Wait. Is that a spelling thing? Is that what, because you spelled it differently, you spelled it 2 different ways? Is that what you're talking about? Why does the second one have a U? Wait. How do I normally spell it? I feel like sometimes I've spelled it with a U too, but it's weird to see it in one sentence. Both spellings. Is Canadian Labor Day a different day? You spell it with a U in Canada. How Canadian? How Canadian? Good old Canada. That's where they spell things with extra U's. It's the same day. Did you have it off? I hope you enjoyed the fruits of your labor without having to deal with any labor. But yeah, I did nothing. And I did like a little bit of prep work beforehand so I wouldn't have to deal with any like food outings. I got a big old pizza from Costco the day before. So yesterday was pizza and Pop-Tarts. What a nutritious diet for Breakable, pizza and Pop-Tarts. Slept in for the most of it. Yeah. I woke up at like 11 a.m., but then I just stayed in bed and went back to sleep, and then I didn't get out of bed till like 1 p.m. Excellent lazy Labor Day. And then what did I do? I did like apply to some jobs because I've been looking for new work. Belle could use a raise. Belle could use some more money. Belle loves money. We all love money, right? So Belle was taking a look at some other jobs. But other than that, I played gacha all day. Gacha game. I think I have an addiction. I also spent maybe more money on gacha yesterday than I probably should have. That's why Belle needs the raise, is because the gacha monster is stealing all my money. More money to... Yep. Exactly. More money for streaming and gacha. I have some stream upgrades I'm prepping to do monetarily. But those... I think I need to save a little bit more. But until then, we're just fine anyway. But yeah, happy Teaching Tuesday, everyone. I can't wait to talk about more radar stuff. Because I think, was it 2 weeks ago now? I think our last lesson was also on radar stuff. It was phased array antennas, the fancy like multi antennas that are just a bunch of little tiny antennas that add up into like one big steerable antenna. But yeah, I'm excited to talk today about more radar stuff. I sort of know a decent amount of radar stuff, but it was never something I learned in school. It's just sort of stuff I picked up, through work or just like researching on my own because I think it's pretty cool. I think it's pretty cool of a topic, and there's like a lot to it. So I'm super excited to share. Super excited to share with you. One second while I switch the scene. Ba-ba-ba. Boom. I think that looks right. And tablet seems to work. Hello world. I don't know why that became a thing. The whole hello world like programming thing. But it seems like such a standard nowadays. Such a standard. A classic. Timeless. And today's lesson will be probably a little bit on the shorter side. I didn't really time it. I didn't even like do a full complete lesson plan. I just sort of know what I want to talk about. It was some old tutorial and people just went with it. Huh. And like, is that really the origin? Is someone made a tutorial and then all the tutorials after that included Hello World? Because I feel like every freaking learning or study or like teaching thing on programming starts with Hello World. But like, there's no way it was like the world's first program was like Hello World, right? Someone's like, let's just make this screen show Hello World. That'll be an amazing demonstration of the world's first program for a computer. I don't even know how that would work, because I think that the first computers were like, you like punched holes on paper and then it read the inputs somehow. I don't know how it outputted things. I'm sure it had a way to output things. An example program in the C book. The original C book. That must be so old. That must be so old. And now we've got all the crazy other C's. C sharp, C++, C whatever. I think there's other ones that I'm not listing. I'm sure there's other ones that are. 1987. Back when the dinosaurs roamed the earth. Back when the dinosaurs roamed the earth. That was... That's how old 1978 is. I think I said 1987 the first time. But that's ancient history. I can't even believe that there were computers back then. Computers back then were big old room-sized things. But somehow we went through a bunch of scientific black voodoo magic and ended up with what we have today, which are these like nice little personal computers where a bunch of like electricity flows through rocks and then weird stuff happens and then boom, you have an anime girl on your screen. The world's such a fantastic place. Sorry, I need some water. Need to hydrate. It's pretty hot where I am. I've been sweaty all day. It's so hot outside. I went for my normal walk, like, at the front lawn of my office building, and I got all sweaty. All sweaty. Gross. Super gross. We got rocks to think of anime girls? Exactly. Exactly. But lightning through rocks and weird things happen. That's my favorite description of electrical engineering ever. Okay, let's start. Okay, so last week we talked about how radar was like, you have like, ooh, I need to make my pen smaller. Rookie mistake. The same mistake I make every freaking Teaching Tuesday. Okay. We talked about how you have like your radar dish, right? It's got some antenna, and that like angles a beam, right? We set it angles a beam to all go one direction so that we can focus our ref waves in a specific direction, and then we can just point at different directions and listen to them all at different times. And then we can tell how far things are, right? So if you have your radar here, you might shoot a beam this way, and then a beam this way, and then a beam this way, and then a beam this way, and you're just gonna listen for the reflections when they come back. And depending on how long it takes the reflections to come back, that will tell you how far away something is in that direction. But it's a little bit more nuanced than that, because I'm fine where I am. Let me know if I need to move my model, by the way. I don't know if I need to make myself smaller, but I think for now it's good since I'm working mainly on the left side of the page. But it's a little bit more nuanced than that, right? Because first of all, as well as we can manufacture these radar dishes, and as precise as we can be, right? In order to get a perfectly straight beam, we'd have to have a really perfect parabola and a really perfectly circular emitter in the middle that shot the radar, the RF waves, you know, super perfectly and bounced super perfectly so that they'd all go perfectly straight. So practically, it is near impossible to have a truly perfect, only straight beam. So really, beams tend to go out a little. They actually tend to get a little wider. But also, this isn't the end of the world, because if you think back to our premise of shooting in different directions, right? If we have a perfectly straight beam, and we're shooting it, you know, a finite amount of times, right? Because you need to send out individual pulses of RF and listen for them individually. It's not continuously spraying out like a constant stream of water. We're spraying out like individual pulses. So think of like shooting a ball in each direction and waiting for it to bounce back. If you go really far away from the antenna, right? We're talking like hundreds of miles, because radars can go like 200 to 300. I think some radars go even 400 miles, right? If you're 400 miles away, and this radar is shooting only perfectly straight lines, there's a very strong chance you're just going to miss your target, because that object is going to be between the lines, right? Because at 400 miles away, even if you're doing like a tenth of a degree every turn, you're still gonna end up with gaps, because your radar beam is only, you know, however many feet wide your antenna is. So we don't want a perfectly straight beam, because then we're going to have all these gaps in between. What we like is we sort of like that cone. Now I'm super exaggerating when I make the cone this wide. It is actually very thin, but it's not perfectly straight. It does get bigger, and that's really important so that we don't have gaps in our radar. So normally when we look at radars, we quantify these spreads. I think they're called radar radiation patterns. Don't quote me on that, but it's something like that. But we normally chart it with a big circle meant to indicate like all the directions. So this is like 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then it goes all the way back to 360, right? So if the radar is pointed this way, what we do is we talk about how wide it is and how strong it is in each direction. Because it, of course, is going to be the very strongest in the very middle of its main beam. It's going to branch out a little, but it's going to be a little bit weaker towards the sides, right? So what you end up with is you end up with this shape that looks like this. Generally, you actually tend to end up with some side, we call them lobes, that also go off in like more drastic directions to the side, right? And we can chart the entire antenna's pattern for every direction and say, oh, it's the very strongest here where it's facing, and it's slightly weaker off to the side, but it's still there. And then sometimes in very drastic angles, it's still there, but it's really tiny. And this is also generally done in log scale. So this point where it is the biggest is like way bigger than even the sides of the main beam. Okay? And this is really helpful for us, because when we talk about how we track things, right? If we track something and we have our radar and it shoots its beam outwards and it gets a return. All it knows is it got a return from this beam, from this pulse. So we know how far it is from the timing, but we don't actually know which direction it came from. It could have come from here, or here, or here, right? It could have been anywhere within the beam. So what we did, because we want obviously to be able to track things with radar, is we found a way to check which direction it came from by sending multiple pulses using this diagram, right? Because it'll always be a stronger return if we hit it with the center of the beam, and a weaker return if we hit it with the side of the beam. So what we did is we set up a system where our radar would shoot multiple pulses. We'll say the first pulse was like this. The second pulse was slightly altered. And then the third pulse was further off to another side, right? And we'll say our object is here, solidly in the middle of all of our pulses, right? Because it's in the middle of the first blue pulse. It's within that region. It's within the region of the second green pulse. And it's also within the region of the third pink pulse. But we can compare our returns, right? And we'll look at how strong our returns are. So the first return, we'll say when we got it back, was this strong, right? That was the blue pulse. Our green pulse was probably this strong, notably stronger than the blue pulse, right? Because our object is in the middle of the green pulse, right? In the middle is where we're going to get a stronger return, because that's more close to the center concentration point of our beam. So that gives a stronger return. And then our pink pulse, again, was probably weaker. So now all we have to do is we just compare those pulses and we say, oh, green pulse is where we got the strongest return. So the object is probably closest to where we were pointing the radar when we shot the green pulse. All right? So this is how we did things way back in the day when we first invented radar and we first wanted to be able to track things, right? Because we needed precise positioning of our radar returns, right? So we just shoot several different pulses, see where the strongest return came from, and assume that that was the direction that our object was in. But there's a bit of a problem here, because radar returns are dependent on more than just the beam, okay? So they can be dependent on what sort of air our radar passes through, right? So air, for example, with more water in it, higher water percentage of water vapor will have a weaker return because that water is going to absorb the RF, right? If what we're radaring changes direction or changes speed, that will affect the return because the surface geometry might change, right? Object reflection. Other things, there could be different sorts of noise that affect our return, right? We could just absorb some RF noise from something else out there, right? All of these things are going to affect the strength of our return. So, if some of these things change in the time between pulses, right? And we end up having like really high noise during the first pulse, and that just like boosts it up, suddenly we have the wrong result, because suddenly we think the first pulse is the strongest. So then we think, oh, the object is where we sent the blue pulse. Or you know, the air could change, the wind could blow more water vapor into the beam, and that could make our green pulse lower, and do the same sort of thing. This can basically just confound our idea of which pulse gave back the strongest return and where the object is, because we always track it from the strongest return. So we came up with a pretty clever solution to deal with this. Alright? Instead of shooting multiple pulses one at a time, we created this new system. It's called monopulse. And what monopulse does is it sends, like it in the name, one pulse. Mono being one, and pulse being pulse. But it sends it slightly differently than you'd expect, right? So normally you'd expect just one single beam blasting out. Monopulse radar uses very specific antenna geometry to actually send out two different beams, okay? So we'll say, I mean, I don't think monopulse radars necessarily look like this, but this is just how we're drawing antennas, right? They send out two different beams. One is like this, and then the other is like this. So they're angled slightly differently, and there is some overlap. So the first one, is slightly up, and the second one is slightly down. And in the middle, there's an overlap zone. Okay? So because they're angled differently, if we go back to this chart, right, what you have to remember is each of these beams has that chart just slightly different in terms of beam strength. So we'll draw them both on the same chart for the radiation. The first one was pointed like slightly off to the left. So we'll make it look like so. And then the second one slightly off to the right. We'll make it look like so. So you'll notice if an object were to be slightly to the right, say here, it would be stronger for the blue beam. And to the left would be stronger for the green beam. And like I said, there's some overlap. Technically the green will have return this way, right? Because it does slightly reach out that way. It's just weaker return, right? Because this chart is signal strength, not distance. It should still hit the object. It'll just hit the object weaker. So what we do is we have these two beams, and we shoot them both, and when we get them both back, we compare them, right? So let's say we have an object, and we get two returns. One return is our blue, and one return is our green. But they both return. So that means they have to be in the overlap region. Okay? But we can see, since our blue is higher, that means we have to be closer to the center of the blue beam. So we're probably closer to the bottom than the top. Alright? And that's what monopulse is we take one pulse, we just split it into two beams, and then when it comes back, we compare them both. And since the beams the pulse gets launched at the same time for both beams, it should have the same everything that we talked about as a variable before. Wait, where is it? Yeah, it should pass through the same air. Should have the same geometry when it hits the object, right? Because both beams should hit the object at the same time, launch at the same spot at the same time, and it should absorb the same amount of noise. So both of these beams will be affected the same way. That makes them easy to compare. We don't have to do any mumbo jumbo trying to correct for any of those things. And we just look at what's stronger then. And then from one singular pulse, we can determine, oh, we were pointed too far to the left or too far to the right. Yeah, it is like that, Penbu. I mean, it's a sort of interesting combination thing. Let me do a new layer. I always forget to do this earlier, so then I have to mess with things and paint on... not what I wanted. Okay. Okay, but what I showed was I showed monopulse in 2 dimensions. Realistically, we want 3 directions, right? Because we not only want our radar to detect how far to the left or right things are, we also want to be able to do up and down. So in order to do 2 dimensions, we needed 2 antennas. In order to add the up and down component, we need to multiply it again by 2. So when we have modern monopulse radar, we normally have 4 beams, right? So it's like a top left, top right, bottom left, bottom right. Okay? Now, something I haven't talked about that we need to be able to differentiate these different types of beams, right? Because if we can't tell the difference between the blue beam's return and the green beam's return, and the green beam's return, then we can't do our little math subtraction and compare them, right? Because we have to shoot them at the same frequency, so we can't differentiate them by different frequencies. Because if we shoot them at different frequencies, they're again going to be impacted by different things, right? Because water in the air will reflect different frequencies at different amounts. Reflections from our object will reflect at different amounts for different frequencies. We're gonna have to deal with a whole bunch of things that will change the signal strength through different frequencies. So our 2 beams need to be the same frequency. They need to be the same timing. Right? All of these things need to be the same. We need a way to differentiate that. So how we do that is we use a thing called polarization. So again, if we look back at our idea of the antenna, and RF waves are really just electromagnetic waves, right? So in some sense, they should be like sine waves for a singular frequency. They're technically, you know, when we use radar, we have much more complex waves so that we can track which pulse is what. We encode like different information under the pulse. But for simplicity's sake, we'll just show sine waves. So what we can do is we have different antenna geometries that do what's called polarization, like I said. So what that would be is one wave would be vertical. And then we need our second wave to be unaffected by the first, right? We need them to be completely independent. Otherwise, that's gonna, again, confound our results. So what we have is we have a second polarization called horizontal, which you can sort of visualize, right? They have to be 90 degrees from each other. In order for them to not interact with each other, right? They need to be orthogonal. Excuse me. But I just mentioned that in modern monopulse radars, we need 4 beams. If they all need to be orthogonal and we just did vertical and horizontal, what else is there? There can't be any sort of diagonals, right? Because a diagonal is just going to affect both. So what other sorts of polarization are there? How else are we going to differentiate it? We actually do have other sorts of polarization. It's a sort of weird idea. We have RF beams and polarizations that don't follow what you'd expect to be traditional, like vertical or horizontal. They're called like clockwise and counterclockwise. And they're sort of helical. I don't know the word for it. They're sort of helical, right? And these, again, manage to be orthogonal from the first ones. I don't think I should draw them on top of each other because it's already getting pretty busy. But we'll have what's called clockwise, which spins one way. And then counterclockwise, which would spin the other way. So what we have to do is we have to shoot 4 different beams, all with the same signal. All with the same signal, the same frequency, same amplitude, so that we get the proper adjusted returns so that we can compare them. And we need to polarize them all differently. So we have a blue polarization, a red polarization, a green polarization, and a pink polarization. And then when we get them back, what we're doing is we're comparing all of the returns to gather information on which direction within our beam, within our beams, plural, which direction within our beams, plural, the object that's returning is. And how we do that, of course, is, again, it's just different subtractions, right? So if you want to know how far left or right it is, what you do is you add both the left and you add both the right, and you subtract them from each other, right? So that's one comparison. That shows us left, right? We're just comparing the beams, the strength of the beams from left and right. And then if you want to compare how high, like how up or down it is, you check the top and the bottom. And you do the same thing, right? You add both of your tops. And you add both of your bottoms. And then you subtract them, right? And then whichever is stronger, again, is which direction it is. So doing all of this, we can shoot one single pulse of RF. It's through 4 different beams, so I feel like one pulse is maybe, like, not what you'd think of, but it is really one pulse. It's all shot at the same time. And we can gather a complete data set of where an object is, right? We only have to shoot one pulse and wait for it to return, because these comparisons give us how far left or right it is. These comparisons give us how far up and down it is, and the timing. The timing, of course, is how far away from our antenna it is, right? Because the timing being how far our object is from our radar tells us how long it took for our pulse to go there and bounce back. And then that divided by the speed of light gives you the time. Okay? So that's monopulse radar. That's how I think most radars have been since... I think monopulse radar is like 60 years old at this point. It's pretty old technology, I'm not gonna lie. We've had this since like the 60s or something like that. But this was our creative solution to dealing with those issues of, you know, air quality changing or geometry changing. And then back in the old days when we shot out a bunch of different pulses and we compared them, sometimes we'd have issues telling, you know, which direction things are, just because we'd have different attenuation on our returns. This also coincidentally makes it harder to jam. Not that anyone's trying to jam radars usually, but, you know, occasionally, you know, some people have bad intentions and they for one reason or another don't want to be tracked on radar. And what they do is they normally just blast out RF back. But when they blast RF back, it's usually not polarized the way that we polarize it, right? Or they can try and polarize it, but the chance of them polarizing it perfectly is not necessarily the polarizations that we have. So yeah, monopulse radar. It's a pretty creative solution to a problem that I suspect most people probably would have never thought we'd have, right? Between, you know, different pulses giving back different return strengths and that screwing our ability to track. But this is how we fixed it. And I think it's pretty cool. I don't know about you guys, but I think it's a pretty cool idea. And it's really interesting to me because it's not super complex, right? There's like some nuanced topics of like the different polarizations, right? But really all this is like we shoot out a couple and all we do is we subtract them. All we do is subtractive. No crazy math. No crazy math. We didn't need any, like, fancy-pantsy calculus. Nope. No crazy analysis. Nope. All we do is we just boop, boop. Minus, plus. Easy math. Easy math. But I think it's pretty cool. It's a really neat simplification to how we were doing things before. Where we were, like, sort of machine gunning a bunch of pulses out and then sort of hoping that the strongest pulse was the right direction. Is it harder to implement than the multi-pulse version? I don't think so. One sec. I don't think it's more difficult to implement, because really all we're talking about is we're talking about changing the shape of the antennas. That gives us the different beams, and then you have like a tiny bit more processing, which I said, which is just, it's just, they call it, I think it's called the magic T, is what does like all your addition and subtraction. It's really just like wires that literally fuse the signals back together. I think it is much more difficult, to be honest, to have really precise comparisons of multiple pulses. I mean, I wouldn't say it's necessarily more complex to implement multiple pulses, but to be accurate, it's more difficult, right? Because there's just so much more at play, right? You can't remove as many factors as easily. But of course, there's other fancier tech we have for antennas too, right? There's so much more to this than I can tell you, because I'm not an expert. And like I said, this is 60-year-old tech, so I'm sure we have crazier, cooler things now too. Like what I talked about, I think 2 weeks ago. 2 weeks ago, the phased array antennas. I think that's way newer. I think phased array antennas are still like 80s or 90s tech. The phased array antennas are 80s or 90s tech. That was tech that definitely really required some stronger computation to get all the perfect timings down for all of your antenna elements. But that's also like a whole nother scale of implementation. That is definitely way harder to implement than monopulse. Just even at a manufacturing level, the phased array antennas. Modern phased array antennas are like, you need whole factories to make the little chips, the little antenna elements. But yeah, I hope you guys could learn something. I hope you gained some knowledge about this, and I hope it's interesting to you. Because I won't say radar is my favorite topic, but I think it is. It's pretty interesting to learn about, you know, how people created solutions for these things. And again, it's not necessarily, it's a solution for a problem that maybe you wouldn't think about. It's definitely not a problem I thought about until someone was like, "Hey, Bell, look at this. This was actually a problem way back in the day." And I was like, "Oh, I had no idea, because I never considered it." Wait. My hairband came out. One sec. Okay, so... yeah. So, it's pretty... when you dive into the more nitty-gritty of it, it's pretty interesting, because they've got, like, crazy equations on, you know, how radar should perform, right? They have, like, what's called the radar... I think it's called the radar range equation, and that includes all sorts of different factors, including literally the attenuation of the air, the reflection of your object, right? The timing it comes back at. It covers all that stuff, and that's some interesting math going on. And again, it's like oddly simple once you think about it. You're like, oh yeah, that makes sense. You just have like a multiplier for air attenuation. You have a multiplier for time return, right? Or not time return, object reflection, right? But of course, everything when you see the equations is like, oh, that makes sense. Gravity is defined by the mass of object 1 and mass of object 2 divided by the distance. Yeah, simple, but like imagine being the first person working on it and that equation doesn't exist yet. You have to sort of think up what needs to go in the equation. But there's lots of cool stuff, right? There's other stuff in radar like Doppler. Doppler is one of the ways that we deal with finding speed on things that we're tracking. Right? There's all sorts of techniques that people use again to like try and fool radars. You can try and fool radars with different ways, like I said, like jamming. Jamming for the original multi-pulse is like a very real threat. That's really confusing for a multi-pulse if it's just reading really strong returns at random times. It has no idea which direction to point. Yeah, exactly, Penbu. Having the foundations that, engineers and scientists before us laid is an incredible advantage. Right? Because way back in the day, the ancient Greeks who didn't have all these fancy tools at their disposal, I think they would find a lot of the stuff that we find simple very complex. And then we've got other cool things. We have computers now. Frickin' computers make everything so much easier. Because there's just math that we literally would never be able to achieve without computers. But yeah, how are we for time? My software engineer friend, he recommended a game for me because I was asking him about how software and firmware interact and implementations and all that. He recommended a game for me that said he would help me learn, right? Called Turing Complete. I think maybe for the rest of the stream we'll spend some time playing that just because I want to learn. I think it should be pretty interesting. I don't know if you guys have heard of it. Yeah, proof by computer checking is real. But it's also... Sometimes computers are wrong, and that... that can cause issues. Let me see. Boop, boop, boop. Cha. Let's see if I can get Turing Complete running. So I know from what I saw on the Steam screenshots, I know it starts off with some stuff I know, like gate logic. Do. But my understanding is it gets more abstract and ends up at a point where we finally get to assembly code. Which is where I feel like I really lose the thread. I don't understand where it turns from... Oh my god, the sound. Loud. Okay. I feel like I generally lose a thread with computers at where it goes from being an electrical thing to a coding thing. So I'm really interested in learning about that. Let's see. Do. And... source... Okay. Y'all can see, right? Da, ba, ba. I guess we'll use the game music and kill the background music. Wait, why is this? My freaking OBS does this stupid thing where sometimes it captures and then it just captures a freeze frame and then I have to like refresh the source. Frick. I guess I'll just do display capture again. Why is this always the issue? Alright, whatever. A signal flows from input to output. In the upper left corner, under input, there's a green icon. Click it to turn the input component off. Notice that the output component is turned off. This is because signal stopped flowing. Okay. Makes sense. Normal stuff. Impressed with how well you completed the last test. Thanks, that was very difficult. The good old turn it off. And not even turn it on again test. Alright, you've decided you are probably not a plant. Thanks. I'll show you a plant. In this level, the challenge is to figure out how the NAND component works. Be sure to figure it out before you complete this level, or you'll get stuck on the next level. Okay, already know how that works. So NAND is only on when both inputs are off, right? Or, no, only off when both inputs are on. Sorry. Because the AND is only on when both inputs are on. And this is just the opposite. Okay. Okay, what does an AND gate do? This is... Okay. Green. Green. Red. Red when both inputs are green. Okay. Okay. Stats? Why does it have stats? Yes, NAND gate, very powerful. Basic building block of everything. Now that you've unlocked the NAND gate, it's time to build a circuit, okay? Last level, you made the table that describes the circuit. In this level, you build the circuit that matches the table. Okie dokie. Using NAND gate, build the NOT gate. Interesting. How do I place... How do I place a NAND gate? Oh, here. Okay. Okay, so we have our input. That gives us... Okay, so we need something where when the input turns on, the output turns off. So we need a second input that's perpetually... green? Does perpetually green work? What if we connect it to the output? Nope. Okay, how do we create a second input that's perpetually green? Also, how do we delete these things? Doop-de-doop-de-doo. No, not what I wanted. Not what... Oh, here we go. Input, wait. Or wait, do we just... Wait, actually we just put the input to both. The same input to both? And then... If we toggle... Yeah, okay. Duh! I'm so dumb! Why am I so dumb? Okay. Built the NOT gate, click next to use. Where's the next? Next. Onwards! Okay. Whoa. Okay. Level map colors complete, available. Oh! Oh! Okay. Alright, this looks like some serious progression involved here. Okay. The elephant is dominating all the other test subjects from Earth. Us and elephants. Us and elephants are the smartest. Okay. Create a circuit that matches the table. Okay, so this is... If they're both off, it's off. If one is on, it's on. Okay, so this is an AND gate. That's really easy, because all we do is we do... Wait, how do we add a second input? Where's the second input? Oh, okay, there's 2 dots from the input. Okay, all we do is the NAND gate, right? And then we add a NOT. Okay, because the NAND gate is an AND just knotted. And then we knot it again to turn it back into an AND gate. Easy, I think. Correct? 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 Correct, okay. AND gate unlocked. Most creatures on Earth are aggressive and cannot focus. To succeed, you must learn to think logically while not destroying things. I'll destroy things if I want to destroy things. Okay? And this frickin' Beavis and Butthead guy is not gonna stop me from destroying things. Create the circuit that matches the table. Okay. So if they're both off, then we get an output that's on. And then if there's anything else, then we get that an output that's off. Wait, is this not just the NAND gate again? Hold on. And not. And wait, no, this is a NOR gate. Because yeah, everything has to be off for the output to turn on. Okay, so how are we doing this? So how do we get an OR gate? Because I would want to do an OR gate and then a NOT gate after it. So let's think. You have one input and another input. And if they're both on, then the output needs to be off. Hey Mystery, we're playing Turing Complete. It's this actually might be really good for you. Or it might be really interesting for you. This is a game that is completely, from my understanding, the complete build-up process from individual logic gates to a full processor with assembly code and everything. So there's a lot of logic going on here? Hi, Ellie. Oh, set the category. Thank you, Ellie. Thank you for reminding me. Turing complete. Updated. I think. I hope. If not, then rest in peace. Not a video. Not a video, Ellie. We are playing a game. How do we want to do this? Wait, do we just do... If we just invert all our inputs to our NAND, does that give us what we want? Okay, invert it. Okay, so inverted NAND. That gives us green. With one, nope, that's not what we want. But we do have... Okay, wait, so if we invert both the inputs to our NAND, that gives us OR. And if we have OR, that means all we have to do is make a NOT after it. And that gives us NOR, which is what we wanted. Right, so if they're both off, our output's on. If one is on, our output's off. If the other is on, our output's off. And if they're both on, our... Okay. So, NOR is just you NOT both inputs to the NAND and then you NOT the output. And that's NOR. Ellie, are you studying this? Are you studying logic gates in school? It's been a while since I've done logic gate problems. Both of you, Ellie and Mystery, if you think this is interesting, you might want to look at this game. It's called Turing Complete. Okay. So, click our button. Bam, 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 bam. Easy. Easy clap, guys. Easy clap. Okay. You should be happy you get to participate in our glorious tests. Okay, Mr. Alien Beavis and Butthead guy. Okay. Sure. I'm happy. I'm gonna be happy to beat your ass. A chance to communicate with very advanced people from the galactic civilization. Alright, frickin' you with your fancy astro turtleneck. Create a circuit that matches the table, Computer systems... Is that computer systems I or computer systems 1? De Morgan's Law? I don't know what De Morgan's Law is, Pen. I feel like I've heard of it, but I can't remember. I can't remember what it is. Okay, so this is... Wait, this is what we just built. This is the OR. Okay. So if both of our inputs are off, it should be off, and everything else should be on. If anything is on, it should be on. Or if any of our inputs are on, it should be on. So that just means we do what we did with the NOR, but without the NOT at the end. Easy, easy. I could have studied ECE. I could have been an electrical engineer. I chose to be a mechanical engineer just because I wanted to be broader. Oh, fancy. So De Morgan's laws are like literally laws written out between all of those things. Interesting. Okay. Create a circuit that's always on. That's easy. We use an OR. And then a NOT from the input. So that way, either way, if the input is on or the input is off, right? If the input is on, then we power the OR through the input. And if the input is off, we power the OR through the NOT. Easy. Boom, boom. Your first manual page, this one is important. Make sure you understand it. Wait, what's a manual page? Alright, Penboo. Alright, you win this one. You win this one. The truth tables for the 4 fundamental gates are symmetrical. You can convert them between them by inverting the input or inverting the output. Okay. You can get from any basic gate to any other. At most, you have to NOT both inputs and output. You can go between or NOR by inverting. Negating the output flips all the bits in the last row of the truth table. Okay, I mean, I feel like that was really wordy for what it was. Alright, what do we got? Next level. We're frickin' crushing it. As you know, these tests culminate in building with a functioning computer. Species that are capable of finishing this are considered sentient by law. Does that mean... Okay, guys. Chat, I need your opinion. Are monkeys sentient? Are freaking dogs sentient? Are elephants... Like, I feel like all those should count as sentient. Maybe not. Maybe my understanding of sentient is wrong. But I feel like they should be counted as sentient, and we all know ain't no monkey or dog building a functioning computer. Maybe my understanding of the word of sentient is wrong.
Yeah, you're a monkey.
Say it again. Say it again. I've got the band hammer ready. I've got the band hammer ready. What's the matter?
Yeah, you're a monkey.
Life is pain. Life is suffering. What does this thing do? A sentient one, though? Thanks for the break of love. This implies relation which doesn't say anything about people who don't complete the exercise. Interesting. The main reason we don't... They would have eaten us! They would have eaten us if we couldn't do these puzzles. Output green on the second tick only. Okay. Okay, let's think. Let's think. Second tick only. That's the bottom one? Doesn't that mean... Oh, wait. Okay, okay. So what we need is we need an AND. That AND's the second one, because that's what we want. And we also need it to not trigger if the first one is triggered. So we're gonna not the first one. Right, so if we do the first one, that doesn't light it up. If we do the second one, that lights it up. And if we do both, it doesn't. Okay. Easy. Easy. Wait, was I wrong? Hold up. Hold up. Wait. First one... Oh, sorry. We had them backwards. Dummy bell. It's the other way. So I was just reading the second one as like... The second, I guess, is actually the first input because fancy freaking choices of indexing at 0 or whatever you're gonna say when everything's off. Hi, Ash. Hi, Ash. I did miss you. I did miss you. And I thought about you while I was watching Gundam the Witch from Mercury. We're playing turn complete right now. Which is actually... This is kind of menacing looking. I'm not gonna lie, guys. This is kind of menacing. Maybe we'll do this next Teaching Tuesday, too. I'd be really interested to follow this all the way through and figure out how, like, this builds into a computer. Last level, you built a circuit that was green when we were at the second tick. This level, we built a circuit that is green when we were at the second or third tick. XOR. Okay. We need an exclusive OR. Okay. How are we gonna build our exclusive OR? Do we do I feel like what we do is we do the same circuit that we had last time. I forget how we built the same circuit that we had last time. I feel like we build the same circuit we had last time twice. One for each input. And then we OR them. Yes, we build the same circuit we had last time twice for each input, and then we OR them. That all makes sense in my head. We'll see if that's actually how this works. This is a fun game. I'm actually having a lot of fun already. Right, so if this is... That lights one. That lights the other. If we light them both, that... Okay, easy. They said it was difficult. But I don't think it was that difficult. It definitely for sure was building off the previous one, though. If I hadn't done the previous one, this would have been hard as shit. Remind you of your childhood, you have to play this? Yeah, play it. It's called Turn Complete. I think it costs like $10 or something, which kind of sucks that you have to pay for it, but this is fun. Building a computer with transistors handcam stream? You know, I probably could, because I do know how to turn transistors into gates. I do understand electrical engineering at that level. That would be really intense, though. Similar game online that's free. Create an OR gate with 3 inputs. Okay, but is that just not ORs compounded? I feel like that's just ORs compounded. You just OR them again. More ORs, like a boat. You want to get back to working with microcontrollers? I haven't used a microcontroller since college, Ash. It costs $2,000 in tuition to do at university. You're lucky if your tuition's only $2,000. But Mystery, if you play this game and learn how to turn transistors into a computer, I will teach you. I'll teach you how to turn transistors into gates. That's not really that hard. That's pretty easy. You got busy with other things? Oh my god, it's starting to branch into so many level options. Okay, I'm digging this game though, guys. I'm not gonna lie, I thought this would be sort of boring, and in a sense it's not like super complex, but it's really It's really satisfying. An AND input with an AND gate with 3 inputs. Isn't this just ANDs compounded again? You go AND. So, some of you guys haven't finished your university, which I guess is, you know, pretty understandable, right? Younger people. But for those of you who have, do you remember freaking writing out code for, like, Boolean logic? Where you guys ever had to do pseudocodes in any of your classes, people who have finished university? Pseudocode where you're, like, literally writing X and Y and Z. Painful for the wrist. Really painful for the wrist. Whoops. Bam, 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 bam. Wait. Oh, I used a NAND here. Duh. Freaking dummy bell. I used a NAND when I should have used an AND. Okay. Boom, boom. Thanks for throwing things at me. Have to do exams with codes on paper? Yes. I remember doing that too. I remember my engineering... Frick, what number? Engineering 10? Engineering 20? Was intro to MATLAB, and we had to freaking do code on paper. But it wasn't even pseudocode. It wasn't pseudo. It was like, she's like, write the actual function you would use to like transform this matrix. You had to have proper syntax in your handwriting. Thankfully, your exams were digital. Good. I don't think I had many digital exams because I was not a computer engineer. Your girl was mechanical, so instead she had to deal with the death that is thermo. Crazy calculus. Crazy calculus. And solver programs. I guess we did have to use computers, because we had to do, like, we had to use MATLAB to come up with, solutions to those crazy calculus problems. Java's the worst language to exist? You'd rather write an assembly? I don't even know. I don't know how either of those languages look, so your girl is a complete dumbo on these topics and cannot speak to them at all. Okay. Create the inverse XOR known as the XNOR. Okay, I mean, that's just the XOR and then not, right? I think. I mean, that's literally what the XNOR is, right? Boom, 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 boom. Okay, so a lot of these levels are like a little bit trivial, but now we finally passed basic logic, and now we're into... What section is this? This is arithmetic. Okay. Okay, let's do it. Let's do some adding circuits. This level is your favorite pastime, converting decimal into binary under time pressure. Wait. Why is there time pressure? Why is there time pressure? Toggle the bits in the panel so they add up to the decimal number in the question. Click here to turn on timerless accessibility mode. Oh, it's actually time pressure. Shit. Okay. 1 in binary, done. 2 in binary, done. 3 in binary, 1 plus 2. 13 in binary, 8 plus 4 plus 1. 6 in binary, 4 plus 2. 11 in binary, 8 plus 2 plus 1. 12 in binary, 8 plus 4. 1 in binary, 1. 14 in binary, 8 plus 4 plus 2. 22 in binary, 16 plus 4 plus 2. 21 in binary, 16 plus 4 plus 1. 2 in binary, 2. 4 in binary, 4. 19 in binary, 16 plus 2 plus 1. 31, 16 plus... all of these. 3 in binary, 2 plus 1. 2 in binary... it keeps going back to easy ones. 32 is 3 plus... or 34, 4 plus 1. It was close. It was close. 32 plus... bam, 32. 7 is 4 plus 2 plus 1. 38 is 32 plus 4 plus 2. 42 is 32 plus 10, which is 8 plus 2. 38 is 32 plus 6, which is 4 plus 2. 14 is 8 plus 2 plus 4. 18 is 16 plus 2. 47 is 32 plus 8 plus 4 plus 2 plus 1. 71 is 64 plus 4 plus 2 plus 1. 121 is 64 plus 32 plus 16. Oh, 1, submit! 11 is 8 plus 2 plus 1. 96 is 64 plus 32. 109 is, oh god. Nope, not that. Wait, frick! We only made it to level 5. I feel like that was getting pretty hard. That was pretty hard, guys. Harder than all the guys near your mom. Recap. Hopefully you noticed there's exactly one way. Yep.
Not the only thing that's hard.
Yeah. Like I said, all the guys surrounding your mom. Okay. Binary eraser. Okay. What else we got? Oh my god. We are so technologically advanced. We have machines to fold our socks. Sorry, that did not go where I thought it was gonna go. Yeah, we have, whoops. Okay. We have machines to fold our socks. What do you mean cute? I'm not cute, I'm evil. Unfortunately, the circuit that detects sock pairs broke on the machine. It probably broke because somehow in the machine you always lose socks. You always end up with one stray sock that does not have a mate. Just like me. This level has 4 inputs. Output green when 2 or more of them are... Don't overthink this level. Guys, I'm overthinking this level. 2 or more of them. Huh? I feel like we do a bunch of ands. We do ands for every single possible pair. And then we OR them all. That's what I feel. But I feel like that is that will work. That will certainly work. But that is very complex, because it said don't overthink it. That is 3 plus 2 plus 1, 6 ands. This is certainly more complex than it needs to be, I feel like. Belle, X, or Ash? What do you mean Belle, X, or Ash? Shouldn't it be Belle and Ash? Huh? Shouldn't it be Belle and Ash?
Me and your mom.
More like you and every other guy on her. Ah. Oh my god, this is so complex. This is so complex. Think of how much capacitance there is in all of these freaking wires. Like, there's a lot of capacitance in all these. This is so inefficient. I wonder if this is actually how we're supposed to do this. God, the fan out. The fan out on those inputs is massive.
It's over 9,000.
It's over. Your mom's over 9,000. Pounds. And how many times she's been pounded. I feel like this... did I super over-engineer this solution? I feel like I super over-engineered this solution. Oh, we have something wrong? Why do we have something wrong? Why was this one wrong? Oh, it's because I connected this wrong. Okay, I didn't have an architecture issue. I just had a connected the wrong wires issue because we have so many freaking wires because because it's so goddamn. We have so many freaking wires because it's so goddamn overly built. What do you mean you can't believe I'd pound your mom 9,000 times? Of course I would. Of course I would. Because I'd pound you 9,000 times. And the apple doesn't fall far from the tree. Using a maximum of 3 components. Output green only when an odd number of inputs are green. Only when odd numbers of inputs are green? That's 1 or 3. And we only get 3 components? Wait. This level has a hint you can use if you get so. Okay. What inputs do we want? Chat. Do we want 3 input components or 2 input components? I'm already starting, Ash. You just don't know it yet. Okay.
4 your mom components.
Also, I didn't even fucking notice that person a couple minutes ago whose name it does not deserve to be mentioned. who was that? I didn't even see it, Ellie. I need a mod. I'm not sure if I should ban that person or not. You see, Ellie, my freaking auto mod stopped you from sending that message. So I don't understand how their name got through. Okay, odd number signals. What if we do NANs? How do we cover so many permutations with only 3 components? Does it count as 3 types of components or only 3 components? Oh, only 3 components. Shit. Okay. I don't think we want an OR. Not a 3-input OR, at least. Because that will rapidly destroy our ability to tell the difference between 3 ons and 2 ons. Okay. So we don't want ORs, because ORs destroy some level of information. And we need precise amounts of information. We need something that will preserve how many inputs there are. Preserving how many inputs there are comes from exclusive OR. Let's do 2 exclusive ORs. And let's... Okay, so that means one of them turns on if any single input is on. And what we want is if they're both on, the output needs to be off. So we need another exclusive OR. Does this fulfill our requirements? We just do 3 exclusive ORs? Boom, 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 boom. Looking good, looking good. Come on, please. Oh yeah, oh, we're the best. We're the freaking best. That's why we have the PE license. You'll preserve my input? That sounds gross. I don't wanna, I'm not sure I wanna know what that means. Yeah, you're darn right, Ash, I am the best. Penpu, I probably won't report it because I think it's one of the other viewers, but... I mean, I felt like that went without saying, Ash. Alright. Cool. Onwards. What else we got? What else we got? What is this one? In our education system, we traditionally teach by tricking students into doing the wrong thing and then tasing. Literally me. Someone may have missed the subtlety. It wasn't subtlety, it was implication. Because I'm the best at everything. Outside of bed and inside of bed. And by inside of bed, I mean building pillow forts. pillow forts to house a pillow princess. I'm not sure if it benefits the students, but teachers love it. Just like my professor, Professor Marks freaking love to tease us. You want a pillow fort? Come over, we'll build one together. Create a circular dependency. This is a circuit where the input of a component relies on its own output. In a circular dependency situation, it is not possible to determine the output of a component because you would first need to determine the input, which will... This state is normally not allowed in other levels, but in this level the goal is to create it so you understand what it is before going up. I mean, isn't that just this? Create one involving at least 2 components? Okay. Easy. It's actually... Quick lesson. We'll just build a freaking... memory. All we do to build... Chat, if you... Those of you in computer science or electrical engineering... Building memory or something that will store an input is really as easy as making a loop of circular nuts. And then they'll just maintain whatever you put in them. Fun fact. Fun fact. Alright, what else we got? What else we got? They'll become sentient. Your mom became sentient. After I was done with her. That's how enlightening it was. The output component of this level is a binary counter where the first 3 pins correspond to 1, 2, and 4. You don't want to weave your own RAM? What does that mean? Is that a thing? Circular nuts? Penbu, I feel like nuts are circular now. Besides the nuts that are all over your mom's face. Thanks for the hydrate. Thanks for the hydrate. You should also hydrate because you're clearly a thirsty girl. The old magnetic core memory? Wait, is that literally just it relies on the inductance to maintain its current? That's pretty... Is that how that used to be? Output of this level is a binary counter where the first 3 pins correspond to 1, 2, and 4. Wait, what? Okay. Use the binary counter to display the number of signals. Okay, so 1 is... I feel like this is all exclusive OR, right? It's... exclusive OR. Yeah, it tells us if we light up those. Wait, I lost count of which one we were on. Okay, this should be. Okay, this should be. Oh, they have a writing tool now. I think. No. Oh, it's just for writing on wire? That's not helpful. I feel like that's not helpful. No. Okay, so this connected 1 and 2, this connected 1 and 3, this needs to connect 1 and 4. This one needs to connect 2 and 3. This one needs to connect 2 and 4. Oh my god, this is going crazy. Wait, I realize that I have lost the thread of what I'm supposed to do here. Because really what we want is a counter that counts all the inputs. So it's not... Oh man, we fucked up. Alright. We fucked up. I should have known this was too complex. So 1, 2, and 4. 4 will only be on when everything is on, so that's 2 ands. That is the only time 4 will be on. Okay, so that's our 4. So how do we set up a 3? How do we set up something to count? Wait. Frick! Frick! Are you sure water won't help, Ash? Is there another type of fluid that'll help? Huh? Maybe you should try Gatorade. Or maybe there's something else. I don't know. You should probably get drinking though. Frick. Okay, so we have the 4-bit. How do we get the 2-bit? The 1-bit is just... the exclusive OR again, because that's if it's odd. That's the 1-bit. So how do we get the 2-bit? We get the 2-bit if... How do we get the 2-bit, guys? What are we thinking? What's the plan? We need a... The 2-bit only turns on when either 2 or 3 of the inputs is on. Two or 3 of the inputs. AND gates? Lots of AND gates? Okay. If we... 2 or 3 of the inputs is on. What's our means of checking this, guys? So if we have 2 on, that makes both those those first exclusives, eh? Two on makes either them both on or both off, right? Yeah, both on or both off. Three on puts exactly one of them on. Okay, so if they're both off, that's fine. Frick. How do we know when 3 are on? What's the characteristic of exactly 3 being on? The characteristic of exactly 2 being on Wait, actually, is there a characteristic of exactly 2 being on? No. Shit! Shit! I'm struggling here, guys! We have the 1 bit, which decides whether it's odd. Done. We have the 4 bit. What's the 2 bit? 2 bit is only lit when 2 or 3 of them are on. But not all of them. We could do ors for everything, and put in logic to make it not happen when all 4 are on. But then we also need logic that will make it not happen when exactly 1 is on. What does it look like when exactly 1 is on? Exactly one of the XORs is lit. So when exactly one of the XORs is lit, do. Is there any other time when exactly one of the XORs is lit? No. Wait, yes. Shit! Frick. Shame it isn't on sale, skill issue. I mean, it's not super expensive. It's expensive for my brain power, though, because holy cow, my brain is overclocking. Hmm. Okay, so I figured out how we can do the 2-bit. The 2-bit is we OR all the inputs, and then we make it not happen when there's only one or when there's all four. And I'm just trying to figure out how to compute when there's only one. Hmm. Adder circuit, but the adder circuits, you know, with place values, not just counting. I remember adder circuits as... Oh, whoa, shit. When I remember adder circuits, there was a pass and then 2 inputs. And then basically what it was is, if there was, both inputs were lit, then it would light the output. If only one input was lit, then it would pass. And then if no inputs were lit, then the output would be hot, cold, off. I'm struggling. How do we compute if only one input is lit? Wait. Do we compute if only one output is lit by doing all the ands? Inverses of and everything, right? So NAND everything and then not it at the end? I need to check this. This is kind of brutal though, because this is already like a really intense circuit. Think of all the parasitic capacitance. Okay, then we AND them all. Nope, that's not what we wanted. Frick.
Time for me to touch grass. Reed, go for a run.
Go for that run. Get the body moving. Burn those calories. Don't die of overheating, though. Shit. Why is it so... Okay. What if instead of ANDing everything, we OR inverses of everything? Right? do the same sort of shit that we did before. And then we invert. Fuck. That's 2. There must be something. What are we missing? How do we calculate if... We either need to calculate a way for only 1 to be lit, or we need to calculate a way for 2 or 3 to be lit. I feel like it's easier to calculate a way for only 1 to be lit. How do we know? So if we use the ands again. Where's the ors? No, we don't want ors, because ors destroy information. We need either AND or XOR. What about NAND? If we NAND them, what happens? We NAND everything? Does that show us... Huh. If we NAND everything, that gives us only 1. I think. Let's see. Light 1? Wait. I'm so confused. Why did that not... My brain is melting, chat. But we're gonna beat this level before we end stream. I refuse to admit defeat. What do we have? What did we build in previous ones that would help us figure out if there was only 1 lit? Okay, if only one is lit, then these two XORs are exactly one lit. Right? Shit, but that's also the same output as if 3 are lit. What am I missing? Okay. If we and... What if we and those? If we and 2 NANDs, what happens? When only one is lit? I'm struggling. We NAND all our inputs. Okay, Penboot, so the circuit at the bottom, I'm trying to create a circuit that only lights hot when exactly one input is on. And the reason for that is... Well, the overarching thing I need, of course, is I need I need to find a way to know when to light the 2-bit. The 2-bit is only lit when either 2 inputs are on or 3 inputs are on. I've determined that I can do that by... Or was it... How was I doing it? Was it ORing everything and then subtracting the times when only one is on? Something like that. Oh, man. Yeah, when only one is on is what I was trying to do. And now my brain is fried. What kind of circuit lights only when exactly one is on? Um... We put in a bunch of knots. And we and them. What happens? Now I'm just trying shit. And that's bad. But I guess that's also how some things work. Oh wait, I know how to do it. I know how to do it, I think. You do exclusive ore for all of them? Wow, this is gonna be a big freaking circuit. Oh god. That's 6 exclusive ores. Shit. I guess we already have 2 instated up here. Oh god. Oh god. Oh god, this is horrible. But if you want it to light up when there's only one, you do exclusive ores for everything. I think? Wait, no. Maybe I'm overcooking. My brain is overcooked. No, if only one is on. If only one is on, it is not this circuit. Because this circuit also is on if 3 are on. We could weave some ands in there. And then make a secondary thing. Frick. Oh, shit. That's not what I want. This is what I want. Okay. Is that maybe I'm overthinking this? Maybe we shouldn't be trying to find a way where only one lights. We need to find a way where either 2 or 3 lights. Two or 3 lights is really easy, I guess. Oh wait, I fucking overcooked this so bad. I know it needs to be done. Okay, this is our bottom will be when everything is hot. That's our bottom, that's our 4. And then what we have is many ands. Shit, that's 6 ands. Oh my god, it's so much fucking parasitic capacitance. Okay. This is 1, 2, 3, 4, 5, 6. Oh, we have too many. That means we can delete you. One, 3, 1, 4, 2, 3, 2, 4. Thank you, Glans. Thank you, Glans. How are you? 3, 4. Okay. So this circuit... Okay. This circuit will light if multiple are on. Right? Oops. Frick. Frick. Middle circuit lights if multiple are on. Now all we need to do... Right? Yeah, that's correct. Okay, now all we need to do is we need to make this not light at the same time that the 4-bit is lit. Okay, which means we do exclusive OR with the 4-bit, and that gives us our 2-bit. Holy cow. Holy cow. We fucking... This was so intense. Oh! Oh! Guys, I think I need a new pair of underwear after that one. Holy cow. That was such an intense circuit. You say that... Wait, what do you mean, actually? What do you mean, actually? Huh? Why are you surprised that we're doing engineering on an engineering channel? Huh? Conklins? But we're actually playing a game. It's called Turing Complete, and we're slowly building up the logic to build a complete processor. But holy frickin'... Thank you, Glenn. This was so painful. This was really painful. I'm just looking at it and feeling pain. Just looking at it, feeling pain. Okay. I think, though, holy cow, we've been streaming for 2 hours, 10 minutes. I think it's probably a good place to end it. We're gonna play more of this for sure. Next Tuesday, at least, maybe earlier. This is really fun. I'm having a lot of fun with this game. I'm having a lot of fun with this game. So we're gonna play more of this for sure in the future. And then we're gonna learn how to build a complete computer, I guess. But alright. For now, we're gonna call it a night. We'll be back Friday, 9 p.m. normal weekend stream time. And then Saturday at noon Pacific, we have a collab with Penbu. And then later that night, we'll have our normal Saturday stream time too. So yeah, I hope you had fun. I hope you enjoyed the stream. I hope you guys have a good week, and I'll see you this weekend. I'll see you this weekend. Don't miss me too much. Don't miss me too much. Goodbye. Goodbye. And have a good night.